Welcome, everybody. Good afternoon. So I'm Coaxter, and this is Max Singularity the Sixth, first of his name.
Hi.
I'm sure you're more familiar with him. And it is now time for us to shift from our personas in the game to some of the luckiest jobs in the world, because we both work for NASA.
That's for
awesome.
sure. Yeah.
I work at Marshall Space Flight Center, and he works at JPL. I help design things like life support systems, small satellites, rocket engines, actually build rocket engines. I'm a theoretical astrophysicist turned rocket scientist turned thermal engineer, so I've had a lot of fun. So welcome. And basically want this to make a full Q&A. This is not a talk to you, it's a ask us anything you want. And hopefully you can, I know in this environment, this community will get lots of fun questions. So first we'll kind of jumpstart things. We've got a couple things that have happened in science and things that are relevant to EVE. Since there wasn't an EVE is real panel this year, this is sort of a makeup for it. So why don't you start off with
my name's Charles White. I play Max Singularity Online, and I do work at JPL. However, I help the rocket scientists. I myself really am not, but close enough. So I am a human behaviorist is where my degree is, and I'm in a field which is relatively young within the last 20 years, which is called knowledge management. And as a knowledge manager and a knowledge specialist and worker, I work for the chief engineer and the chief knowledge officer. And what that really means is we do spacecraft investigations where we learn from our trials, and we create a lessons learned. So if you actually go to the internet and type NASA lessons learned, you can see my actual work there when you search under the topic of JPL. I've done lessons learned on ground facilities like the battery fire that occurred in Madrid. I've done lessons learned on Mars Curiosity rovers. And so knowledge management is also how we move information back between junior employees and senior employees. So I'm really one of those jack of all trades, master of not a single thing. So I can field a lot of the general questions. But when we also talked this morning at breakfast, I'm a hobbyist expert at relativity and general relativity, and I can. I am working as announced with CCP. I guess I'm going to also be the Stephen Hawking's of New Eden now. So because I am
shoes to fill.
Yeah. So I am going to explain how. The submarine physics of EVE, and there's going to be a real model that you can now go, oh, now I understand why you stop and go through planets. So,
Right. So kind of jumpstart things. First off, does anybody in here recognize this image, this data, this picture? Yeah, all right. Okay, this is a Nobel Prize in the waiting. So as I said, I was originally a theoretical astrophysicist. This is what we've been waiting for a long, long, long time.
Yes.
This is gravitational waves. We've detected it for the first time. To give you an idea of how important this is in the astronomy community, this is like never seen light and now suddenly seen light.
Oh.
We have an entire spectrum to see.
Not Pope. Yeah.
Stay in. And so we are going to be able to investigate. We have no idea how much of the universe using this. So these particular curves here, what they represent is we have two very large facilities, each L-shaped, each 4 kilometers long in each direction in 2 places in the United States. And they saw this lovely wave, and this represents 2 intermediate-sized black holes, only about 50 times the size of the sun, so not that big, that collided and coalesced. And this is cool in so many ways because this is something that's always been hypothesized about for a long time, and now we finally actually have proof of it. And you can't even tell in the image very well, but there are multiple curves there where the model is fit on top of the data. And in the third line, there's the residual, and it just it nails it. So this means our understanding, a theoretical understanding before we actually saw any data was just darn good. Now, the reason I bring this up in the context of EVE is, switching gears a little bit, is to sensors. All right, everybody knows how many sensors we have in the game, right, for the 4 races. We've got LiDAR, which exists in real life. We've got that. We've got radar. That exists in real life. We've got electromagnetic, magnetometric, and that actually exists, too, in real life in a limited fashion. It's used for detection of things like submarines. And number 4 is gravimetric, which up until now we had no idea actually had any, we theorized it, but we didn't know it existed. We now proved it.
EVE was first.
Eve was first. So I think that is really, really, really cool. I don't know of any other game that sort of did that and kind of predict. Now, of course, if you have a 4-kilometer long array on a tiny frigate, that doesn't really work as a good detector, but we'll work through those details later. So with that,
but we're also 23,000 years in the future.
True.
So when we talk about our technology, it's trying to like giving a magnet to a caveman and going, that's a special rock.
it takes a little work to get further.
Yeah, yeah.
So like, for example, in the detectors that we have, the gravitational wave detectors, they have to measure something and see a change in a length over these 4 kilometers that's less than the size of a proton. So that's sort of the level. It's 10 to the minus, the ratio is 10 to the minus 21, which even to astronomers tends to be kind of hard to grasp that many orders of magnitude. So maybe we can improve it in a few thousand years and get a bit better.
Yeah. And what I love about it too is it's also to Einstein's, again back to relativity. In measuring this, we use the speed of light as our constant, and how we measure it is the changing, the warping basically of the distance between as the waves are coming in on an L-shaped sensor. Mm-hmm. So this is a large. I'm looking at him because he actually knows more about this.
He's a manager.
Yeah, I'm a hobbyist. I'm knowledge manager. He's a real scientist. So by the shifts of this, by just small.
Yeah, they measure a strain basically, and the ratio is 10 to the minus 21 is a strain that they measure.
So that's how we're able to detect that, and then we calibrate that with the speed of light, which is a constant, and thus we get these
in vacuum.
In a vacuum.
So this describe why it was such a hard. So this data comes from LIGO. Sorry, we just assumed that. Everybody sort of knew that, which is a very large collaboration. The paper that this is taken from has about 1,000 co-authors on it. Huge collaboration over many decades. And what it is these 4 kilometers each are under extremely high vacuum. And so these long tubes, and they're just basically shooting a laser beam back and forth, and they're using a laser beam based on assuming the speed of light, which doesn't change in a vacuum, how long it takes, and therefore what the distance is. And so they measure the change in that distance, and the way gravity waves work is they're basically a little distortion, so things get pushed and pulled a little bit, and if you see the correct distortion, the right time in the 2 different facilities at the same time, well, not the same time, but the proper delayed time, then you've got a signal. So with that, I'd like to open it up to basically ask us anything you darn well please, space related. And,
shields up.
Yeah. Go.
I've read about the EM drive and how multiple different and it seems to produce thrust. And do you guys think it's actually working? And what kind of missions will we be able to use it for if it does work?
Well, as a physicist, my kind of skeptical answer is no. Because it does violate law of momentum, so it's a probable no. But just as you asked that, actually, just the other day, a report, I think it was a news article actually, came out that said that actually there is a theoretical, let me back up a second. General relativity, Einstein presented an equation. He did not present a solution.
Yeah.
Okay, so general relativity, actually, we don't know what the correct equation is, we just know what it has to obey. And so there's an infinite number of solutions, we don't know which the right one is. So some of the offered solutions have some interesting properties. One of them has a property called Unruh radiation, which is kind of a way of saying that things, when you push, you can only push in discrete pushes. So it's kind of like photon quantization, but for inertia. And based on that theory, they can come up with an explanation for the EM drive. Okay, both of those, as a physicist, I am very, very skeptical of, but not a 0% chance. And if we could use it, that basically means you have no fuel. You don't need any fuel. And for rockets, the tyranny of the rocket equation, as we call it, is you got to bring your fuel with you. And as soon as you say that, you're limited.
Because now you have mass.
Because you got to take all that useless mass.
Add 2 gallons, have double mass, and so forth. I myself, the way we do science is we're skeptical. It's like, really? That's cute. Show me more data.
Yep.
And so basically, if us two came out with a theory that says, hey, we have a new uber-duper drive, all of you Eve players would say, yeah, really. And that's what happens in the real world. Every university, Caltech, MIT, all the way around. I remember when cold fusion came out, Oh my gosh. Everybody was like, oh, this is the breakthrough of humanity. We can finally get the Amarian the drives to power flight. And there was actually an announcement over the intercom at JPL. It was like, bing! With new cold fusion research, please remember to follow nuclear protocols and safety. Contact the safety office for protocols of testing. And it was like, oh yes, JPL is testing cold fusion. And what did they find? Nope.
Yep. I was at Caltech at the time when that paper came out, and immediately we all kind of sat around shredding the paper, just looking at it like, really? So,
yeah.
And trying to find, because that's the way science works, is you see these wonderful, extraordinary claims and you need extraordinary evidence. But you don't disclaim it, even if you say, that violates everything we know. We still have to take a look at it.
And we are in the information age with the internet, but we're also in the misinformation age of the internet. So, and we're in the sensationalization age, where everybody is like, oh my God, there's an alien space station around a star, so it's alien technology, stuff like that comes out. So watch for the actual research papers. NASA is...
That's a very good rule of thumb. Is when you see it on the interwebs, or you see it if you see it in a refereed science journal, which actually the EM Drive has appeared in a couple times, that kind of gives you a degree of what the community is thinking about it.
Yeah, not just Snopes.
All right, next. Okay.
Yeah, you have those two really good detectors for gravities, but can you actually pinpoint where it comes from?
Not yet. With just two, they were basically able to identify the hemisphere it came from, because you can't do any finer resolution than that. But it is intended that these will become observatories if you have many of them. It's very similar to VLBI in radio interferometry. Sorry.
Yeah.
Where by having many, many stations, you eventually are able to turn it into an observatory and not just say it's coming from here, but to take an image. So once we get many of these observatories, that's why this is like a brand new window on the universe. Because if we have more of them, we start figuring out where it's coming from. We start figuring out images of what they look like. It's just mind-boggling. So yes, behind you.
How many people at NASA play Kerbal Space Program?
There is actually on the internet, and I've passed it around a couple times in the office. There's a cartoon I saw where there's a young engineer and an older engineer, and there's a whole bunch of scientists around the table, and she says, I told you do not cite Kerbal during the review.
I would say for those who are actually making the real thing, the number's probably lower.
Yeah, it's probably lower.
Any other questions? Anything about the universe? Take a pick.
With regards to your new missions and the whole goal of getting to Mars eventually, and mention of the restraints on budget in the United States at the moment, what kind of willingness do you find internationally, the international community and the other space agencies to want to kind of like jump aboard the bandwagon and help out in these projects?
The willingness is there. So there's a lot of willingness with the international partners. Believe it or not, many of the nations around the world have space programs. Now, I was multi-processing, so you saw my processor go slow. How many saw my presentation yesterday on building? Oh, thank you. Okay, so for those who haven't, we were talking about there is no lull. And because we're not, launching shuttles doesn't mean we're not that we're not building a space program. And there's a lot of nations around the world that have space programs, but they don't launch anything. They're actually building. They're working with their industries to make components and pieces.
So a lot of the space missions we already have, for example, are often joint missions where they provide an instrument and we provide a launch vehicle or something like that. So it's an ISS, of course, is the International Space Station with a lot of collaboration. So there's a lot of willingness to work together and provide pieces here and there.
Yeah, and like I said yesterday, we're still +10 blue with Russia, when it comes to space. So
having worked with them a little bit, I'd say +5.
Oh, okay.
We do need to negotiate things a lot.
Yeah, but
like on station, where it's actually very interesting because they have different data, historical database, and a lot of space research, science human exploration is based on your own experience, and their experiences are different from our experiences. So they'll come to different conclusions than we do, and then we have to say, okay, well, we have to agree on it, and so we come to negotiate a conclusion.
This would probably be a good time for the disclaimer.
Thank you.
The opinions, political opinions of us as players of EVE Online do not necessarily reflect the national space and
Aeronautics in space.
is that what it is?
Yes. We actually do in aeronautics.
Caltech or JPL.
Personal opinions only.
Yes.
Can you say something about the relationship NASA is having with SpaceX, and to what extent technology will also be reused, shared?
The short answer is it's really good, actually. We and SpaceX work together in terms of an oversight, in terms of sort of sharing, because the idea is to take off from NASA some of the things that you might say are easier, perhaps not the right word, but that's been done before sort of repeatedly, and hand it off while we can then focus on things like going to Mars. And SpaceX is doing a great job of that, and we kind of iterate with them, kind of a little bit of looking over their shoulder. It's the oversight role to say, is this consistent with what we need for space station? Is this consistent with what we want for astronaut, crew situations and things like that? And so we work pretty closely with them to make sure that everything gets delivered the way we want, and it's been working pretty well. In terms of sharing, sort of, it's a company, so they do proprietary things, and as long as it's not important for us to know those details, then it's theirs.
So you can Google NASA Commercial Space Program, because we have an actual arm of NASA that is just collaborating with our commercial space partners. So it's kind of like CCP has partners as well. So we've have our partners with the commercial space, and that's part of the roadmap to Mars. Because what we want to do is have the commercial partners with multiple capsules going to the space station and servicing it, keeping the space station up and running. And that way, NASA can then focus our attention on the farther frontier. There's some way up at the top, yeah.
That's actually an interesting story. I graduated from Caltech, and I actually worked at JPL, and I was actually at JPL about the same time he started, and I never met him.
It's a big place.
It's a big place. And during that time, I decided I wanted to I was an observational astronomer working on the Deep Space Network at the time, and I decided I wanted to go back to school for theory work. And so I went back to graduate school, still working at JPL. And in academia, there's kind of a hierarchy you have to go through to get in academia, which was my goal at the time. And so then you do postdocs after you get your degree. And so I was doing postdocs. I did one in England, and then I did one in Los Alamos in New Mexico, which is familiar for doing slightly different things to most of you. But they had really, really fast computers, which they let me use to do black hole modeling and things like that. But in the process, I started learning some engineering, because my background up to that point had been pure theoretical, so I was learning a lot of engineering stuff. And then NASA announced the Constellation program, which some of you may be familiar with. And I said, the U.S. has not built a brand new rocket from scratch in a long, long time, and I want to get in on it. And so I jumped ship and joined NASA to work on what's called the J2X engine, which was going to be the workhorse for Constellation. And then it was canceled. So now we have SLS.
Space Launch System.
Space Launch System, which will be our next rocket, which will be launching in a couple years.
Wink, wink.
Which will be launching in a couple years.
Yes.
And so working on that a little bit now, as well as say life support stuff for if we go out into deep space, what we have for life support now is not adequate. We have to actually improve it a bit and come up with new, better designs so we can stay out there for a year or longer with minimal maintenance and things like that. So then I started working on rocket engines, basically. And the common thread between all those subjects is I'm actually really at heart a computational physicist. And what's really kind of interesting is that all of those fields, and so now I also do thermal designs for spacecraft, is they all involve fluid dynamics. And so basically that has been my common thread. Those sound like very, very different fields, and they really are. But the common thread is I've always done fluid dynamics of one type or another, black holes, turbo pumps in engines, in rocket engines, fluid flows on spacecraft, and now fluid flow for life support systems.
That's just awesome.
It's pretty cool. Like I said, we've got awesome jobs. Yeah?
There's a couple more up there.
What are your thoughts on the idea and concept of orbital tethers?
Of what? Actually, I don't know if you're familiar with the e-sail. So the short answer is it's cool. Tethers. There have been some spacecraft attempts, various experiments where we've been trying to spool out very long tethers. And as you might imagine, it's got some engineering difficulties that need to be worked out. But there's a neat little concept that actually came from Finland that NASA's trying to work on called the e-sail. So you've probably heard of solar sails, where you use the photons from the sun to push something. Well, the sun also shoots out something else other than photons. It has the solar wind. It's got ions. And so you can use those ions to propel something by having, if you have a long strand, basically, of something, and you put it at a potential, then it'll suck up ions, and every ion that it sucks up, it's depositing its momentum to that strand. So if you attach to that strand a spacecraft, you can propel a spacecraft. And the very cool thing about that is when you work out the math, what you find is, as everybody knows, when you go far away from a light, it gets dim pretty fast. And when you go far away from the sun, the solar push that you get from the photons drops off as r squared. And so that means it's really hard to use it when you're out in the outer solar system. But the solar wind only drops off as 1 over r. So that means if everything else is equal, you can use that to go to the very edge of the solar system and beyond. So it's a very promising interstellar travel method. So, actually, it does have tacking issues. You can't go backwards against it. But yes, sailing boats of various kinds. The wonderfully recently announced idea, basically sending gobs and gobs of tiny iPhones, basically, and you basically give a laser push to the impulse. You launch them up in LEO, low Earth orbit, and then you shoot a bunch of lasers at them and rapidly accelerate them in the direction of a nearby star. The idea itself is, like I said, we know solar sails or hitting a sail with a laser will propel it, so it's fundamentally sound. The question I would propose is if you have a tiny iPhone that's 4 light years away, how good's your reception? It's very hard. Now that's today, right? And if it takes a long time to get there, we might have very better receivers because the Deep Space Network that JPL runs has 70-meter antennas. But they would have a really hard time picking up a signal from an iPhone at Alpha Centauri. But if we had a bigger, better DSN, we might be able to. So it's not out of the question.
Or a possible space-based DSN as well, because we've talked about that as well, putting arrays in space and doing that as well.
Yep.
Do you think the possibility of using additive manufacturing, or for those wondering, 3D printers, is going to help with the ability to actually basically build satellites in space as opposed to having to send up a whole satellite as well?
Indeed, we've already started some work on that. We've actually certified some additive manufacturing rocket parts that for the SLS that is taking extreme temperatures and gas outputs on those. So those are working really well. This is what we call disruptive technology. Disruptive doesn't mean it scatters it. It just means, we have to retool, or we have to change how we're doing business. So we did upload. We flew up to the space station version 2 of a 3D printer, and we are actually looking at 3D printing CubeSats. And CubeSats, I just had a couple of meetings the last couple of weeks at JPL. That if you look at the CubeSats, they've kind of had they're coming out of the hobbyist academic world, and they're actually being taken more seriously for missions and commercial missions as well now. And there still are some limitations, like the iPhone communication problem, so forth, and the size of the instruments that we can put on it.
They're this big. They're very tiny.
Yeah, one unit is this big, and you can actually attach a 3-unit one together. And so we're researching and experimenting with printing at least the cases out that would hold them on the space station, and then all we have to do is just open the window, get a breath of fresh air, and throw them out.
And in fact, the first SLS launch will have as its payload, because it's a test launch, so you don't put people on a test launch, it will be a lot of CubeSats.
Yep.
Because one of the says that the reason to believe that the universe is infinite. Do they really mean, are they serious about that, or is it just a convenient say that it's very, very
terminology.
That the
question
universe
here,
is
but-
what?
Is it, what
It-
do they mean when they say that, for example, when the universe is infinite?
It's infinite.
Oh, the best analogy, it's overused and kind of hard to wrap your head around that I can use is a surface of a balloon. If you're a two-dimensional, think of flatland. If you're a two-dimensional being on the surface of a balloon, where does your surface end? It never does. It just.
Say that it has no end.
So we do not know what the value of k is yet. Sorry. So we don't know if the universe is called open, flat, or closed. And what that means is if it's closed, then eventually the push of the universe expanding is too weak for gravity, and it eventually collapses into a big crunch. Or if it's open, which means eventually everything will just keep going to the point where you're infinitely far away from everything. Or if it goes flat, which is a very just nice balance between those two. And strangely enough, I mean, a priori, from a particle physics and cosmology perspective, it can be anywhere. K, it could be minus a bazillion to plus a bazillion, and yet strangely, it's really close to zero. In other words, it's really close to flat. And this is it has been a long-standing puzzle for we just don't know why that would be, because a priori could be anything. And so that says that the universe is not doing either this or quite this. And if dark energy turns out to be truly an additive expansion, it might push it to the direction of this, but we don't know for sure yet. So it's hard to say in terms of the end, where does it end or where is the center? It's hard to explain in that there isn't a center. There wasn't a beginning as such. We can just roll back the clock to the point where we don't know anything more, and that's what we call the Big Bang.
Or the other one is the big freeze. Because if it comes back together, you get maybe another Big Bang. But if it goes way out, all the stars have a limited amount of fuel. And that fuel definitely will burn through. And we're not talking just 15 billion years here. We're talking trillions of possible eons. But there might be, in that model, one day when the last star shining in that universe goes out. Whoa.
Yeah. long, long, long away. Just make sure. Far, far away. Far down the road.
Not our problem.
Anybody else?
I'm a Girl Scout leader, and in the UK the curriculum is quite restricted in terms of what you can teach kids. From my point of view, I'm looking for activities that can get them involved, particularly in the Mars stuff, because before coming here, ask them about it. We're talking kids that are 10 to 14 year old, they've got NASA debt, NASA's
Right.
involved, they've got
NASA was not canceled.
NASA, yeah. Nope.
Not even
Nope.
lulled.
suggestions in terms of where to go to look for activities,
The-
things that get them invested.
Well, the NASA.gov webpage actually has a lot of links. Even though we are not the Department of Education, we actually have a lot of educational materials for just that sort of thing for all various ages. So you can start there.
So grab your iPhone and make a note. It's called spaceplace.nasa.gov. And I don't think it's spaceplace JPL now. I think it's spaceplace.nasa.gov. But it's a site that's laid out for different age ranges for kids, so high school and preschool and so forth. And it's NASA is very good at, even though we're not the Department of Education, we're very good at trying to get this information out as much as we can. To me, it's kind of frustrating that when I see people saying, that we're aware of all these conspiracies and we're holding information. Oh, no. If we find something out right away, we're going to publish it as soon as possible, because if we don't, all those other space agencies will. And so there's a race to get it.
We actually have a public server, which everything we do actually goes on. And so anybody from anywhere can access.
Yeah, and that's one of our major shining points is our outreach. So the resources are there, and you can download them. Actually, as an educator, there is an educator program where you can ask for details. Now, I don't know about the international abilities where we send stuff out, but you could ask. Especially for the educators in the United States, we can send you some resources. But I'm just not aware of the international conditions.
Yesterday you showed some very nice presentation about the upcoming plans for the whole asteroid gravity stuff.
Yes.
Are there any plans
Nothing. Well, so everything is in our pre-phase A. So we're talking about it with concept studies quite a bit. But again, it's not. Nothing is solidified yet. There's no solid funding plan for it. But we keep bringing it up. So it's not in our roadmap to Mars as of yet. But who knows? It depends how much, engineering-wise, we could do it.
We could.
So it's not a function of engineering. It's about politics and the will to do it. So this is where the public comes in,
Correct.
and you guys basically determine which direction we go, and then we try to take you there.
Right, because NASA as a federal agency and as administration, basically, we get to a certain extent told what to do.
Yes.
Now, we could say this is what we want to do, and they take that into account, but the politics is a big role in determining what we actually get to do.
Should we vote for Democrats or Republicans?
I believe that would be a very dangerous question to answer, so I will say no
Next
comment.
question. Amarian.
Galente.
Why is there a big push to head to Mars? Like you had said yesterday, you want to stay close to home if something happens.
Yes.
Why not start with the crawl, walk, run thing and go to the moon first, live there, learn to live there, and then go on deeper?
The public, again, the public's telling us, the world is telling us that, it is us as human beings to expand and reach out and go places we haven't gone before. So there are some people who said, that moon, we've gone there, let's go farther. And I think last Fanfest I talked about an author around the turn of the century, 1900, wrote a paper on the morals of war. And in the Morals of War, he says, mankind's not just our culture, but our technology expands because we're in conflict, kind of like Eve. So because we're in conflict, we develop new technology so we can stay safe. And that is the morals of war. And last Fanfest, I say, I want to throw that away. I want the morals of space. In our conquest to go farther and develop new technologies, let's keep going, let's keep exploring. And from those technologies, we have cell phones and Fitbits and things like that. So we have now two models that we can have the morals of technology development. So I'm all for the morals of space.
Take a larger step out of that.
Correct. Yeah, we want to take a larger step out of our safety bounds, and Mars is that next logical step to go to a planet. Venus is no place to raise your kids. It's just,
That's true.
in fact, it's hot as hell.
Yeah.
Yeah.
Yep.
Given an infinite budget and resources, what are the two areas that each of you like to focus on?
I'm going to build an Abaddon.
Come on, put the right hat on. Well, going back to what we got at the moment, so the rockets that we have are kind of limited in terms of the rocket equations. Just the rocket equation, it's got an inherent sort of limitation. We're down to very thin tanks, very light engines, everything. We're kind of pushed it as hard as we can. So a very disruptive change is required to sort of get us out of that. And my personal take is that there are two material science things that need to happen, or one of two, to really get us out of that. One is something very long and very strong that can make a space elevator, which from a physics perspective would work, and once it's there, it would be cheap, and space would be easily accessible. Right now, no such material exists, so that would be sort of number one for me. Another possibility is room temperature superconductors, because that permits a lot of easy transportation, basically. So it could make getting to space much, much, much cheaper. So essentially, the problem, the choke point that we have at the moment is not in space; it's getting to space. So things that work great as in-space propulsion, they're not at this point in time what we need. What we really need is something that gets us off the planet for cheap.
The other problem we also have in space is radiation, period, dot. It is a problem. It's a problem for our electronics, it's a problem for our astronauts, and you just can't put a ton of lead in a spacecraft because it's very massive. So we need more research in radiation shielding from the very hazardous radiation environment as well.
So in yesterday's presentation, it was mentioned that the SLS was reusing the engines used in the shuttle program.
Yes, the RS-25.
Is this the reason why? Is this the best engines we can have right now, and we just need to make this next development in technology, or could we, or was this more of a budget situation? Like we had this already, let's use it.
It's a combination. The SSMEs, Space Shuttle Main Engines, the RS-25, is an awesome engine. It has a lot of capability. It's throttleable. It's very durable. It's a good engine. But if you have it sitting in hand, it's cheaper. So could we make a better engine? Probably. But the balance overall was it was both.
And the other problem is flight certified. So even though we come out with new technology, like a new computer processor, we have a lot of missions that are restricted on not allowing new technology to fly on missions. So they have to be flight certified. So what happens is we have what are called Pathfinder missions that we do technology demonstrations. So that's where we are putting more weight on the engineering of the mission than we do on the science of the mission to test it. And by doing that, we can flight certify something. So these RS-25s are very flight certified and reliable. Out of 135 missions, and I'm not going to do the math on stage because I'm nervous anyway, out of 135 missions times 3 engines, that's 300 plus engines, almost 400 engines.
Don't try.
I won't try. We've only had like 5 quasi little
none of them,
solvable
none of them
incidents that we were able to fix. So that's a reliable engine. So yeah,
it has flight heritage. It makes a big difference.
So yeah, I'm all for the RS-25. And the SLS, we have multiple configurations where we can launch with 3, or we can launch with 5. So we can increase our thrust with that. So it's not a bad choice.
You mentioned room temperature superconducting. There is a website, superconductor.org, who has reported superconducting materials at plus 100 degrees Celsius.
Well, I have not seen it, so I can't comment on it. I would add that it's not just having the room temperature superconducting. There's actual multiple types of superconducting, and it can't be what we've seen in ceramics, which is kind of lower class superconducting. It actually has to be truly superconducting for what I was thinking of. And 2, it has to be in a material that you can actually form, that you can actually do stuff with, make things out of. And both of those are qualities that we don't have anywhere near room temperature. So I would, again, going back on the science hat, be very skeptical without more information.
Thank you. So when we sent New Horizons to Pluto, we were sort of expecting an icy comet and really rapid loss of atmosphere, and it turned out to be a much more complex.
Oh yeah, beautiful.
It's beautiful.
It is beautiful.
Now that we know that, it's going towards another object in the Kuiper Belt in 2019. What are your hopes that we see there now that the lid's off?
Well, one of the cool things is we always get surprised. I mean, it's just, like you said, we expected almost simplicity. Oh, yeah, ice ball. No. So now we're like, well, I don't know. What are we going to see next? Is it going to have organics on it? It's mind-boggling because we still don't understand the details of what makes Pluto look like the way it does. So if we don't understand that yet, we can't really say, well, is the next one we're going to see going to be like that, or is it going to be more like the original ice cube that we thought? We don't know.
So we have 8 planets, and we have 5 dwarf planets. And if back to the unlimited budget, we need some robotic probes to go check those out too. Because those what amazing. Because look at Pluto, how amazing it was. So what does Core or Make have? That. Oh.
We don't know. That's the cool thing. Like for example, there are I don't know. You're familiar with Vonnegut's story about Ice 9, but ice actually water ice actually has different forms. As you get colder, depending on how it was formed, it actually has different crystal structure. And then once it melts, it sort of never goes back to the old form. It's very cool. And so we don't know a lot of the details about those ices because, well, we don't get that cold. We don't have the environment on another planet. So will we see another form of ice that we haven't found before because we're still finding them on a farther out, colder body? I don't know. But yeah, we look forward to it. We're very excited.
Obviously, space travel, what we've seen in history can have sometimes rather tragic events.
Yes.
if the drive after the period of wanting to really get back to work and come, okay, let's put this behind us, let's not let it beat us, keep us down. Is there anything like what brings you all together as a team and
So the question was, for those who didn't hear, is and hopefully I get this right. How long does it take for us after like the Challenger or Columbia, for us to kind of get past our morning stage, and how does it inspire us? Is that pretty good? What gives us the drive to get back to work again? Immediately, and to be bolder in their honor.
And
Gonna make me cry here.
yeah, I'll go further than crying.
No, it means that much to us.
Yes,
I mean,
it means
we
that-
hold that
Yeah,
so dear to our heart, and that's why our safety is also number one too. Because we pull out all the stops. It's like there is, mission failure is not an option when it comes to manned space flight. So we're doing this, and we're going out. So we become more emboldened. And we hope the public kind of joins us with that, because there's a lot of quotes about failure, and like Kobe Bryant says, the man who has accomplished nothing has never lost nothing, So if you want to succeed, you need to keep trying, failing. We have we're looking at new policies where we fail fast, fail often. And I tell people this during my lessons learned investigations, is when we do an investigation, we're not after the who, we're after the what went wrong. And then people then start telling us, oh, okay, well then let's fix this. Because it's not like the Queen of Hearts. We're not out to cut people's heads off because something failed. Because in science, that's what happens. That's what we do. We fail. So we go after what went wrong. Now, in some cases, maybe there is a reason for a who, but those are usually very rare. But we really need to focus on the what. So it makes us more emboldened.
My shorter answer is, for me personally, it's without growth, you die. I mean, you're either growing or you're dead. Those are the only two growth states, and since there's only one place for us to grow, that's why for me it's a very personal thing. I know.
Great question, thanks. You almost got me.
Yep. Okay.
You mentioned that a lot of CubeSats are being launched and they're getting cheaper and cheaper. Is there any problems with them hitting each other or space station or other satellites?
We're very careful about making sure there isn't a problem, but it is one of those many, many, many things that you have to actually go through a checklist to make sure it does not happen. So for example, when they get ejected from their launch vehicle, they have to be ejected in a certain way with a certain timing. So for example, with EM1, the first launch of the Space Launch System, that mission, which will have these CubeSats on them, they also have an Orion test capsule. And believe me, Orion says those CubeSats better not run into our capsule. And so there's various procedures that we make sure in terms of they get launched later, they get launched with enough velocity in the right direction to make sure that it doesn't happen. So we have not had those sorts of incidents because we cover for it.
There's also a deorbit plan for those and life expectancy. So there's like a couple different classes of the CubeSats that are defined. I just had the presentation, so I can't memorize it. But I walk away with this information that at one class it's like within 2 years, another class is like 5 years, and next class it's like 10 years that they will deorbit, and they do that through natural degradation of their orbits through the thin atmosphere.
Just, you were talking about the expansion of the universe and contraction.
Yep.
Just wondering in terms of like black holes, is there any numbers on the amount of space that's disappearing into black holes and the amount of dark matter that's out there in the world?
I'll rephrase that if I can. Black holes are thought to exist fairly commonly in the universe. Pretty much, as far as we can tell, every large galaxy has a very large one at the middle of it, including ours. And it is constantly, they're all constant, to a certain degree, one degree or another, absorbing mass. So they don't absorb space, they just take up mass that falls into them. Ours is not growing particularly fast, but there are some other galaxies called quasars and active galactic nuclei, which are sucking up, the mass of a sun like every second. They're just absorbing all sorts of horrible amounts of mass. And that is a non-negligible amount, but it's not like the universe is going down a black hole drain. In terms of dark matter, there's more dark matter. We think this is all theory since we haven't found the dark matter particle yet. But for all the various motions of various objects in galaxies to work out, we hypothesize that there's matter out there called dark matter, which only interacts with normal matter via gravity, or probably only does.
It's kind of like the caveman with the rock and the magnet is like, how does that work? Wow.
But they can still play with it and figure and try to deduce it by doing experiments with it.
Yeah, exactly.
And so based on that, all the dark matter out there, in fact, I think it was last year, just before Fanfest, actually, I was reviewing a paper that said, if dark matter actually gets dense enough, there's enough dark matter in a region, it will do the same thing that we think happens with normal matter that produces a black hole, but it would produce a possible wormhole, which I found very cool because if you do some of the numbers, some of the distributions of dark matter, it would actually potentially cause natural wormholes between the cores of galaxies.
I want to see the white
Which
paper.
makes me say, Eve-gate?
Yeah. Yep, there's one.
So dark matter was theorized in the 60s and earlier, and it's been a long time. How does that compare to other, like I don't know the history very well, how does that compare to other major questions that we've been trying to figure out actively for that long? Because it feels like we sort of stalled on that question of what is dark matter?
We haven't stalled, as he kind of alluded to. In science, there's a lot of sort of negative results. Failures, he used that word, just negative findings. And we have been looking for what type of particle could be dark matter for a long time. And basically, we have this long checklist of various theories. And we've just been working our way down saying what type of particle, no, it can't be this type of particle, can't be that type of particle. And if we might even get to the end of that list and say, well, our theories are obviously wrong and we need to find another one. So it kind of doesn't really hit the news and we say, no, it's not a supersymmetry particle. That doesn't really get into the media much. But if you hit look at the journals, you'll see that we're actually really pushing hard to try to find it. And
it may take us a century. We might, not be able to discover what it is because we're still in wooden ships on sailing the sea, so we're trying to discover what it is.
The gravitational waves were predicted from very immediately from general relativity theory, so it was a little over 100 years. So it happens, and especially the really disruptive theories like these in terms of really changing our perception of what we can do in the universe.
And I want to give you one last gift from my long story. I'll make it shorter this time. What, me go long? I'm a pope. I like to preach. When you're thinking about speed of light, what is speed? It's distance and you notice he sits back. He's heard this one. It's speed and it's time. Right, so that's when we talk about the speed of light and black holes and how gravity is so tense that the speed of light can't get over. I want to ask you to do this. If you start thinking about speed of light, remember that, but think about this. Start thinking about the speed of time. We're sitting on this Earth in a gravity well that has gravity, but time for us is ticking slower than the GPS satellites. If we didn't account for that time dilation, the satellites on GPS would be wrong, all our cell phones would be wrong, all the airplanes would be wrong. So we actually know this through Einstein and time dilation. And the equations are 100 years old now, but yet we still are not teaching our children about how to think about time dilation. So when you take and design a spaceship model, an engine, let's say, and the engine has revolutions per minute, RPMs, right? Revolutions per minute, that's based on time. And when you have to put fuel in it, gallons per second, that's based on time. The faster you go, the slower time goes. So if you're slower time with your RPMs, the faster you go, your RPM on your car all of a sudden starts to drop. Again, relative, you drive in a car, you're still okay, but everybody else is like, how does he go so fast? Only at half throttle. Not only that, the fuel is not coming in as fast because the engine you can't get the fuel as fast. So when you talk about, the speed of light is just a barrier, it's not speed of light, it's the speed of time. you're actually fighting the time to go through. So I'm not going to give you all of that. I'm just going to plant that seed in your brain, and hopefully this oak tree will come out. And 6 months from now, you're going to go, Max, I get it. That's the end of our presentation, so now we'll ask questions.
Yeah, right.
Yes.
Just going back to relativity and the GPS satellite, is it true that when the military were first planning the GPS, they weren't entirely convinced about this whole relativity thing, so they actually had an off switch to turn it off so that they could do it because they didn't trust Einstein being right about it?
No.
I never heard that, so
No. We knew. This is known stuff. There are some off switches on the satellites for different reasons, but no, we did know about this. And what frustrates me as crazy is these have been known for 100 years, but we're still not teaching properly about the time dilation, because it even gets weirder. The faster you go to in space at the speed of light, not even distance is a constant. Distance changes. So your Titan moving, near the speed of light is 14 kilometers long. When it's stopped at the speed of light, it's like 5 kilometers. That'll mess your head up. Because inside the Titan, everything is relative. It's still 14 kilometers long, but somebody observing this Titan is like, well, that's a scrunched up Titan. So that there's all kinds of weird things that occur like that. But again, there's only one constant, and the constant is the speed of light. Everything else is relative. Yes.
Is there anything else that you would like to see the teaching in like high schools or something that they're not currently teaching?
I'll take that.
Yes.
It's a kind of a pet peeve of mine. I would use the phrase critical thinking. Because that sums up a lot of what I see in fresh engineers, in trying to, and in science. Because in science, that's what science is. It's all about critical thinking. So they tend to either drift to it naturally or have been taught it. But generically teaching in everything from grade school all the way up, critical thinking of all sorts. Because it's helpful across the board. Everything from figuring out that that's advertisement is misleading to that link in JITA is spam or a scam. So those sorts of critical thinking skills to evaluate things across the board. That's why I say please teach logic classes, those sorts of things, just to learn how to evaluate and think about things.
I concur, and we also need to teach. We also need to learn how to teach, because what we found out is everybody learns differently. So we need to understand how different people learn and teach them in that mode. So we need multimodal education, not just education. Exactly, and I'm a prime example of that. I got some guy who takes my DNA.
We have time for one more, I think, before we have to get out of here.
So, change of topic, but what would it look like to be in warp? We see kind of in game we see like distortion.
Yes.
What would it look like?
I got that one, or do you?
Yeah, you can go with that one. You're the,
Okay,
you're
I'll
the
start
special
it, you
role.
can
I'm the GR, you're the SR.
That's true. So when you're traveling warp, your field of vision actually starts shifting a little in front of you. The 360 is no longer this 360. Take it from there.
Yeah, so you can't, you disconnect from certain angles, basically, because the photons can't get to you.
Right.
And so everything is kind of squished. Add to that also Doppler-like effects, so that things shift, blue shift and red shift, depending on which direction you're looking at. So basically everything will get compressed and the colors will become very strange. And when you start going particularly fast, eventually it's no longer the optical, so a star would show up in completely different wavelength, you wouldn't be able to see it. So yeah, it would look very, very odd.
And I'll leak something from the book. Okay, is there any CCP in the room? No, I don't see any. So
It's being recorded.
what you see inside your warp tunnel, you're between normal space, way down here is subspace, and in between there is hyperspace. You can't go all the way to subspace because you wouldn't exist. So you're in a hyperspace and you're seeing the energy from subspace, and that's all I'm going to tell you right there because it's subject to change.